Hello and welcome to what is, I guess, the fourth lecture. So the last lecture, we tried to look at finite groups, and we ended a little abruptly because we were actually saying we got into Lagrange's theorem, and I realized that there was some amount of, a problem with my notes, in the sense that they had not been not been scanned properly or something. So we shall rectify that. And before we go on to doing that, I actually wanted to give you, some references. I think that you guys were actually looking for, but I didn't quite give you. So let me do that before I do anything else. So let's see. Okay, so let me share screen. Okay, so let's me write down the names of the references that I have and will be using. And some of them are on the website, but not all of them are there. So let's see how we do it. Constraint for space, but okay, here we go. So references, and let's list things out. So I think this one is something that I've already told you about. So number one is the algebras in particle physics. This is by Howard Georgi. Number two is going to be group theory in a nutshell. This is going to be by Z. Number three would be group theory. This is called physicist's perspective. Physicist's perspective. This is by Pierre Raymond. Number four would be group representation theory. This is all, okay, for physicists. This one is by Jin Quan Chen. J Bing and Fan Wang, sorry, not Wang. And ultimately, this symmetries, the algebras, and representations. And this is by Fuchs and Switch. What? Okay, so this is a list of references that I promised you, and here they are. Um, okay, just make sure that I am uh, more audible to you guys. Let me put my mic on. Yeah, hopefully that improves it. Okay, so that was the list of references. Now you have them. So let me just quickly go back to what we were doing in this, in the last lecture. So I gave you a list of group axioms. So we are going to deal with finite groups, and I gave you a list of group axioms. Let me turn this thing around. And these group axioms included closure, associativity, the existence of this unit element, existence of an inverse element, and yeah, so that's that. And then we went on to trying to understand finite groups of lower order. I showed you these multiplication tables, and there we saw that there was, if you had a group of order 2, that's unique, this is called Z2. Group of order 3 is again unique, this is called this is a Z3. And group of 4 onwards, things can get more interesting. And there, when you have this group of order 4, you have these two possibilities. The first one is Z4. This Z4 is the member of the same class that we discussed, Z2 and Z3. So these form what's known generally as a cyclic group of order n, where you have these repeated action of one element. Okay, so that was one of the things that you could get on a group of order 4. There's also this other thing which is called the dihedral group, which is given by this this D2 that I showed you here. Okay, so this was and I just briefly mentioned the notion of an abelian group. And I showed you how one could actually get these Z2s to work out. Okay, so I mean the Z. So okay, no, let me rephrase that. One could get. I showed you how one could realize this D2. Now there, I first told you this notion of subgroups, where there's a subset of the elements of a group also form a group. So that's the notion of subgroups. And when we're looking at groups of order 4, we have subgroups. Now Z4 has, for example, a Z2 subgroup generated by E and A squared. D2 actually has 3 separate subgroups generated by EA1, EA2, and EA3. And from there, we express D2 as this direct product of these two, sort of commuting subgroups that we have. So yeah, so that was that. And then I gave you the notion of this, direct products a little more in a more general setting. And this general setting was that you could have G and K, and these could have elements GA and KI. So we're going to assemble, if you wish, new elements, which are these duplets of GA and KI. And the group, the group multiplication would be, governed by this rule, where GA with GA gives you GA star GA, and these two gives you KI star KJ. You can check that these satisfy the group axioms, and they form a group which is order NG times NK. Okay, so NG into NK. So this is called a direct product group G cross K. Okay, so this gives you a simple way to produce new groups of higher order. Now we are going to understand, so this is the part that would have been very unclear from last time around. So let me try and explain this a little, explain this, okay? So now what we want to do is we want to address, when there might be subgroups, okay? So to do this, let's start off with, so a group G, and this group G has elements GA. Okay, GA goes from 1 to n. And now we say that there is a subgroup H in this with n number of, small n number of elements, H1 to Hn, such that, H is in G, okay? Now we pick an element of G that is not in H. So the n elements of the form G1 cross Hi are, elements of G, but not those of H, okay? If that were to happen, if some of them were to be in H, then what we would have is G1 times Hi is Hj, and G1 would be Hi, Aj, times Hi inverse. Now we have already said that G1 is not in H, right? So it cannot be that so we have G1 is Aj times Hi inverse, because Aj times Hi inverse is an element of H. So this, if this happens, then this is going to contradict our initial hypothesis. Okay, first step. Now what do? We are going to repeat this, same sort of process for another element, G2 of the group, which is not in H, also not in G1 times H, okay? So this new set G2 times H1 is distinct from both H's, and also G1 cross, G1 star H's, okay? Again, this is because if they were to overlap, then we would have had G1 cross Hi is equal to G2 cross Hj, and you would be able to actually write down G2 as G1 cross some Hk, which is again going to go against what our initial assumption is. So we can do this, we can go on doing this until we run out of group elements, thus forming this last set, which is Gk cross Hi, okay? So now what we can do is we can write this full group G as what is called a coset decomposition. Now, to be very precise, this is the right coset decomposition. So G will be, all HIs plus G1 star HIs plus dot up to GK star HIs. So G will be H plus G1H plus dot G1, GK star H, okay? In which none of these sets are going to actually overlap with each other. So the order of the group then must be a multiple of the order of its subgroup, okay? So that is what we get from here. So Lagrange's theorem is going to say that if a group of order n has a subgroup of order subgroup H of order small n, then n big N is necessarily an integer multiple of small n. Okay, so this one, it looks weird. So let me try and see if I can. So this little beast that I have out here is nothing but small n. Okay. And this integer k, which is n big N by small n, is called the index of H in G. Okay. So remember this, and it should be obvious by the way that we just discussed this. Okay? So this is Lagrange's theorem. So now what? Now let A be an element of this finite group and form the sequence A squared, A cubed, AK of all the all the elements of K. So since it is finite, all of them can't be not all of this, I mean, would be different, and some AK would be equal to AL, which sort of says that A of K minus L would be equal to the identity element. If there is some AM which is equal to E, we say that this particular element is of the order n. Okay. Now, suppose that B is another particular, another sort of element of G, and this has an order K, then this is going to generate a cyclic subgroup HK of G. Okay. So then again, what we see is that by the thing that we have just proved to you, shown you. So by Lagrange's theorem, then K has to be a multiple of n, which is the order of the group. Okay. Good. So that's one thing. Now, if G is a group of prime order, then we have some interesting things happening here. So since a prime, of course, does not have any divisor, the elements have to be of order either 1 or p. So it has to be that this group G has to be just ZP. Okay. So so for prime orders, life becomes simple, and we do not really need to think about what we have to do for groups of order 5, 7, 11, and so on. All of them are just cyclic groups. Okay. So what would be interesting is, what would be more interesting is, groups of higher order like 6, 8, 9, 10, 12. These would be left to you as reading homework. I expect you to look at this and come back to me, and we can discuss this in one of our Wednesday meetings. Okay, very good. So this was references. Let me go ahead. Okay, so now let's try and discuss more things. Okay, so some other things that we want to actually look at. What is this? So firstly, we are going to discuss something called conjugation. So conjugation is a property that preserves the multiplication table of a group. So now let big G be a group with elements small ga. What we would do is we define the conjugate of any element Ga with respect to another group element G as the following. So Ga tilde is the conjugate. This is G times Ga times G inverse. Clearly, if you are looking at what the group multiplication is, that's simple, right? So that's just, so if you have G tilde A times G tilde B is what is G times GA times G inverse in times G GB G inverse. So these things go away. So this goes away. So what you have is G, GA, GB, G inverse. So if G, as you can see, if GA times GB is GC, then so what is going to happen is this is going to be GC, G inverse. So this is GC conjugate is this. So this is something that you can clearly see is going to preserve this. This group multiplication as we have defined. Very good. So let's get rid of this. So this is a mapping which leaves the multiplication table invariant, and so this is a homomorphism. In addition, so this is since it is also one-to-one, this is a special homomorphism, and this is called an automorphism. Okay. Now we are going to define classes. So what we would do is we would use this thing that we have just said above to organize these elements of a group into sort of non-overlapping sets. So what is this? So what we do is so we look at some particular element GB and conjugate it with respect to all other all other sort of elements of G. Okay, so GB tilde is GA, GB, and GA inverse. So now if you do it for all of these GAs in G, so this is going to be called CB, and this is going to generate a set of set of elements, and we're going to call this a class. Okay, now let's pick another another second element of G, which is not now in CB. Okay, and this forms a new class. So CC is going to be G tilde C, which is again GA, GC, GA inverse for all GAs in H. And these are as I said, these classes are non-overlapping. So we can go on doing this. So CB and CC have no elements in common, because if they did, then it would just imply that GC is in CB, and that is actually going to contradict our initial hypothesis. So we can do this all the way until we have exhausted all group elements. And what we can do, what we can say at the end of the day is that we, for any finite group of order n, this can be decomposed into k classes, where k is less than n. So since this particular thing does not depend on the choice of elements GB or GC and so on, it is unique, and the number of classes that are in a group is actually a characteristic of a group. Okay. What can be shown, this is something that we are not going to do, is abelian group of order n has n classes, and each of the this is something that you can try and prove. That's extremely simple and straightforward, and this particular thing, each of them will just have one particular element. Okay. Yeah, that I think is extremely straightforward to do, and the identity element is always going to be a class by itself, and it's going to be called C1. Okay. Okay, moving on. Let's try and see. Let's try to define a few more things again. So this is an important thing. This is called a normal subgroup. So let H with elements small hi be a subgroup of G. Okay. As I write here, some subgroups have a very special property that if you find what the conjugate of H is with respect to any other element that is in G, this thing actually remains in H. Okay, So G H inverse G is, G HI G inverse is actually a J. This stays in H. Okay. If this is the case, then the subgroup H is said to be a normal subgroup and is sort of denoted by this L. Okay. So this is going to be important when we go on. So most groups have actually normal subgroups, and the ones that would not have these sort of normal subgroups are going to be special, and these are going to be called simple groups. Okay. So that's actually it for this short lecture that we had. I hope I have been able to clarify the problems that we had with Lagrange's theorem earlier. So this was a short lecture, but what we will do very soon is actually we will move on to what are so we want to understand representations. So that is what the next 2 lectures or 3 lectures would be on. And so that's the thing that I have in mind next. So actually, no, just for some reason, again, I have something which is missing. Just give me a second. Yeah, I have things which are not loading properly. So what I'm going to be doing is I'm going to be trying to pause the video here, and I will just get back to you guys in a second. Okay. Okay. I am back with, after even more, if you wish, technical difficulties. But now we are in a situation to actually finish up the part of the lecture that I wanted to do. There was some trouble with this particular file. Okay, so what I wanted to do next is I wanted to talk to you guys about something called quotient groups. Okay. So, so let me just also remind you that these things that I call finite groups are so we ended up this by saying that there are these normal subgroups, and now there are uh, if you have groups without these normal subgroups, they're called simple groups, and it so happens that simple groups actually form the building blocks of all other groups. Okay. All right. Now let's talk to you about quotient groups. So now let's consider the homomorphic mapping of the group onto a smaller group K. Okay. So G goes to K such that each of the each elements GA go to K. Now this preserves this multiplication. Multiplication table. So essentially, if GA into GB is GC, K into KB is also KC. So now let H be the subset of the elements of G that are mapped to the identity. Okay, this is called the kernel of the group. So H is the subset of the group this that goes to the identity. So the set HI that that is an H is a subgroup of G, and what is going to happen is that if you were to look at GH G inverse, that is going to be K identity K inverse. This is going to be the identity. So this again is something that you so that is going to, so this maps to maps to the identity. So H, as you can see, is going to be a normal subgroup. So now let's take this argument backwards. So what we will do is that we will have we will start off with G and assume that it has a normal subgroup H. And what we are going to do is we're going to consider two separate. Uh, so what we would do is we would take any element, um, GAHI and GBHJ of two different cosets, which is GAH and GBH, and we'll form their product. So GAHI and GBHI is what? So what we need to do, so let's sort of try to do this. So we insert some GBs out here, okay? So GA times GB inverse, that's an identity that we've inserted, HI, GB, HJ. Now notice, what is GB inverse HI GB? So this is, just HI, what we will get is the conjugate of HI, right? So this is going to, so now what is the case? So now HI is an element of the normal subgroup H, okay? So this is what we get, and what we see is that the product of this coset has this property that if you have GA, and if you take multiplied with GAH, and you multiply it with GBH, it actually becomes GCH, okay? So this is a property that this product of these cosets, this is going to satisfy a group property as well, okay? The unit element is going to be the subgroup H, H itself. So if you have GA into GB is HI, then what you would see is simply that the cosets GAH and GBH are inverses of each other. So what we have done is we have shown that the group's axioms are satisfied, and now we have a group with NG by NH number of elements, and this particular group is called the quotient group, or the factor group G by H, okay? So this is a homeomorphic image of G, but it's not a subgroup of G, okay? Finally, so let's just do a few more things. Suppose now that H is not the largest subgroup of H, and we split its generators like the following. So we have G, we split this into GA, G alpha, and HI, okay? So that's what we'll. So what are we going to get? So we have. So what we will do here is we will form two separate factor groups. So what we will do is so we will have, yeah, okay. So let me remind myself just a second. Yeah, so what has happened is that we are now supposing that H is not the largest subgroup of G. And so we are going to split its generators like GA, G alpha, and HI. Now notice that so H is a normal subgroup of H prime, where H prime is just given by these H alpha and sorry, G alpha and HI, okay? Now it's clear that we can form two separate factor groups. One of them is, G by H. So that is just going to be GAH, G alpha H, and H. The other one is going to be K, which is H prime by H. So h prime by h is going to give you g alpha of h and h. Okay. Now clearly, what you can see is from here is k is actually a subgroup of g by h. Okay. Uh, since h is a normal subgroup, so you have the, I mean, sort of, I mean, so the conjugation is this actually holds. Okay, this holds, and so thus what is happening is if g alpha, g alpha tilde is an element of h prime, then k is a normal subgroup of this particular g by h, the quotient group. Otherwise, it is not. Okay. So h prime must itself be a normal subgroup of G. Now this may be so let's again say this. Let's So I urge you to sort of go through the steps once more to clarify in your own head the things that I'm saying. So I hope this would be clear to you. If not, we can again go through this in one of the the sort of discussion sessions that we have. Okay. All right. Moving on. So G mod H is a normal subgroup if and only if H is not maximum. Okay. So the quotient group has no normal subgroups as long as H is the maximum normal subgroup of H. So this sort of opens the way, if you wish, for a systematic decomposition of all groups in terms of simple groups. So again, just this, so what is happening? So finite groups, as we said, with normal subgroups are very sort of common, and Galois actually split this groups into two types. One was the simple groups, which have no normal subgroups, and the rest. Okay, what can be the types of simple groups? The one example that we saw straight away, where was cyclic groups which are of prime order. There can be other, so there can be alternative groups of 5 or more objects. We could have this infinite family of groups of Lie type, and there are also things called sporadic groups, which we would get into at some point of time. Okay, so all of these finite groups can be constructed systematically from these simple groups. So that was the idea of the lecture for the day. I'll not go into finite groups of order 6 right away here, but I'll give you some more time to go through this. So yes, so let's hope that I can get rid of my technical problems in the next class, and we will not have to pause things in between. So let me actually stop my sharing for the moment, and the next video is going to be happening very soon sometime. And okay, so it was supposed to be a short lecture. It didn't turn out to be very short, but you're going to get the next one very quickly sometime later in the day today. Okay, very good. Thank you, and see you guys soon.